Hi there, and welcome to the first lecture in BCIT Technology Teacher Education 4044. It's a course based on structures and using the information we learned about material science in the first semester to actually apply that to the design of a variety of structures. And right in front of you here, you see one of the structures that we've designed in a previous year. This is a truss structure. And the whole idea behind this truss structure is that it has to hold a specific amount of weight for a specific period of time. And so here we go right here. They've applied the weight. And of course, this was in a pre-COVID time where we were able, in fact, this was the last thing we did in class before the pandemic sent us all home. But looks like this one is going to meet its needs. Oh, very efficient truss design right there. Here comes another one that wasn't quite so efficient. And you'll notice the mode of failure in there, a lot of buckling in the members. So we'll talk about how that comes about and how we analyze that to see that happen. Oh, there's another one that went. And that must be the last one because it just keeps on repeating. There's a nice one with the buckling on it. Anyways, to get started on this year, you've got some information up on Desire to Learn, our learning management system, and you'll find in week one, the Introduction to Forces section in TTED44, that we've got lecture notes on statics and symbols, and then some lecture problems on forces and moments. And so I'm going to be going through those with you momentarily. So if you haven't had a chance to get online and download those, it'll help you to have the actual document in front of you. So maybe just pause me for a second and go ahead and download those documents and print them out. You'll also see on my screen, I've got solutions to lecture problems right here. And this is one of the neat things about Desire to Learn. This will not show up on your screen until you have completed one attempt on the vector components quiz and one attempt on the moments quiz. So you're going to have to go into your quizzes, and if you want the answer key to the lecture problems, you've got to go on and actually do some of your quizzes on here. So go into your quizzes and you'll find the component vector quiz and the moments quiz waiting for you. Okay, so that's all well and good. And let's bring this device right up here. And there we go. Now I've got my handouts in front of me. And so if you've got this printed out, let's go ahead and let's talk about what we've got on our first set of notes right in here. Okay, so statics, the analysis of forces and structures that are not accelerating. So if things were actually moving, we'd be looking at dynamics and kinematics. But in this aspect of physics, because things are not moving, we are just looking at statics right in here. Okay, so if anyone asks what you're studying today, you can tell them, hey, we're studying statics. And in like anything else where we take a look at these studies, we're going to use some terminology because they cross over from the purely technical field into the range of engineering. And engineers like to have secret codes to try and keep all of their knowledge private. It's not actually why they're doing it. It's just because it's simpler. It's language, jargon. Every trade or technology has it. But this little symbol right here, the Greek letter sigma, capital sigma, if you're going to be fussy about it, means the sum of, and then F. F is going to be our forces. So what we're saying is that if you've got an object sitting right here and somebody's pushing it on it this way with 10 newtons, then if you want it to stay static, somebody better be pushing that backwards with 10 newtons in the opposite direction, because 10 newtons this way plus 10 newtons in a negative direction okay, is going to come out to equal 0 newtons, and our object will not be moving. So if we can't satisfy the sum of all forces being equal to 0, then we're not dealing with statics, okay? We're dealing with dynamics, kinematics, or something else. Now, in addition to having the sum of all forces being 0, we also need to have the sum of all the moments be equal to 0. So we've got these two little formulas that we pop in there. Sigma F equals 0 and sigma M equals 0. So sum of forces is going to all add up to 0, and the sum of all the moments when you add everything up is also going to be equal to 0. So we need to make this all balance out. And to do that, we need to understand a little bit about what we're talking about when we're referring to the forces, and we need to understand what we're talking about when we refer to the moments. And before we jump into that, we should talk a little bit about how things are going to be laid out on here. And for all of our work, it's helpful to think of things being laid out on the Cartesian plane. Now, there is a three-dimensional Cartesian coordinate system with x, y, and z axes, and everything that we're talking about in here applies to a three-dimensional coordinate system, but it's sure a lot easier to simplify our problems down and take a look at them in the 2D Cartesian system, because that gets rid of that third dimension and in the process saves us well over 50% of calculations. So generally, if you see somebody looking at a statics problem, it has to be pretty complex before they solve it in 3 dimensions. We usually want to break it down and take a look at how can we simplify this problem and solve it in 2 dimensions, because that just makes our lives that much easier. Okay, so basically you've used this before in math class, everywhere. I mean, 2D Cartesian coordinate system is everywhere, but just to refer the rules, we've got an x-axis, and the x-axis is positive as you head off in this direction, and we've got a y-axis that's positive as you head off in that direction, and this is our 0, 0 point, so everything over here is negative x, and everything down here is negative y. All right. So let's flip on to the next page there. Now, again, this is something that you've covered in the past and we're just reviewing right here, but let's take a quick look. Two-dimensional grid locations we express as x, y, and we can name these points. So right in here, we've got a point A, and its location is 1, 2, 3 over, and 1, 2 up. So that's point A located at 3, 2. Okay, point B, 1, 2, 3, 4, 5, 1, 2, 3 is 5, 3. And if you're going to draw point C on there, well, that shouldn't be too hard. Just go over -2, and you don't have to go up or down anything. You'll find point C is right there, and you can label that C. And you'll find point D at 0 on the X, so the vertical line up in here, and -3 right down there, and we'll call that point D. This is going to be easy, right? It actually is relatively easy. It's just one of those things that, you start with something easy and then you add something on top of it, which is also easy. And then you add something on top of that, which is also easy. And if you skip over the steps or you skip a layer in your understanding in between, suddenly it stops being so easy. Okay, so now to discuss our forces, we're going to be taking a look at vectors. Okay, and vectors are used for a number of different applications, but one common use is to represent a force. Okay, and what makes a vector maybe a little bit different from a point is that it has both a magnitude and a direction. Okay, so in other words, a value and a heading. So if you were talking about speed as a vector, you might say that Jason is heading 10 kilometers an hour due north. Okay, we've got a magnitude, the velocity, and a direction, the heading. So on here, we're going to draw an arrow pointing from A to B, and we're going to call this vector AB. And we'll put a little arrowhead right on here to show the direction that it's going. And this is how we would refer to that vector because it goes from point A to point B. And it's got two components to it. Okay, and we're going to refer to those components as the x component and the y component. So the x component tells me that it moves 1, 2 places in the x direction and 1 up in the y direction. So our terminology for that would be the AB vector has an x component of positive 2, and the AB vector has a y component of positive 1. It moves 2 that way in the x, 1 that way in the y, and if you do those two steps together, you get your vector. Okay, now this seems really obvious. Like I say, we're just building steps upon each other. And why this is going to be really important is that later on, when we come to doing more complex structures, we need to sum up all the forces to show that they do equal 0. And if we've got a whole bunch of vectors heading off in different directions, that's going to be really hard. But if we break each of those vectors down into its component x and component y vectors, then it's going to make a lot more sense, and we can add them up and we can get to 0 fairly easily. Okay, now, as I said, vectors are going to have a magnitude and a direction. The magnitude of the vector, well, in this case, it's just its length, and we're going to use Pythagoras a lot in here. People have known how to do this for a couple thousand years now, and so we know that a squared plus b squared equals c squared. In other words, you can play around with that with some algebra, and c equals the square root of a b x, the x component, plus the y component, each of them squared. So if I say 2, because abx is 2, and 1, because aby is 1, that gives us a magnitude of 2.24. So the direction of the vector is 2 over and 1 up, and the vector has a magnitude of 2.24. So there's our magnitude and direction for this vector. Okay, so let's take a look at arrow pointing from D to C. What would you call this vector? Express the x and y components of this vector using the correct terms, and what is the magnitude and direction of this vector? Okay, press pause right now, and let's see if you came up with the same answer that I did. Okay, pointing from, did you press pause? Are you back now? Okay, this is how I go about solving it. Pointing from D to C, so the direction matters. So I'm going to draw it coming up this way right in here. Make sure my arrow shows the direction that I'm pointing. So I'm going from D to C. And so I would call this, I'd draw my little arrow right over top, vector DC. Okay, the x and y components of this vector using the correct term. So the vector DC has an x component of -1, -2. And the vector DC has a y component of 1, 2, 3. Positive 3. You could leave the positive out if you wanted. We assume it's positive unless somebody puts a negative in front of it. What is the magnitude and direction of this vector? So now, we sketch in a little triangle here, and it comes up 3, and it's come over -2 plus 3, and we want to know what is the magnitude right on there. Now the magnitude will always come out as a positive number because we square these numbers right here. So the magnitude is going to equal the square root of 3 squared plus minus 2 squared, or the square root of 9 plus 4 equals root 13. And that equals a number that I can't automatically do in my head. Where's my calculator when it's sitting around? There's my phone, that'll do. And let's see right on here. Square root of 13 is 3.6. Okay, now we don't have any units in here yet. If we were measuring in centimeters or discussing things in centimeters or meters, that's fine too. And if 3.6 is the magnitude, then the direction is going to be now, usually with this, we can simplify sometimes. So if our direction had said minus 4 comma 6, okay, these two are the same directions, but this is the simplified version. So that's that good old searching out the lowest common denominator. Okay, so there we go. Some simplified terms for setting all this up. Now, why we're doing all this is because we're going to apply this to forces. Okay, and we represent the forces as vectors, but sometimes we'll name them slightly differently. It means the same thing here. We have a force acting on point A. So you can think of this, you can see that the force is pulling away from point A. So you can think of this as being like somebody holding a string and pulling on this point in this direction. Okay, and so this force has both an x component and a y component, and we call the x component of the vector the force acting on A, okay, x component, and the force acting on A's its y component. Okay, so FAX, grab my ruler right here, is going to be coming over in this direction, and FAX is going to be moving right out here. And the magnitude of FAX is going to be 2, 4, 6. And what is the magnitude of FAY? That's going to be coming down from right here. Now you can either draw it coming down right here, or sometimes I'll say, well, we already came over in the X direction. Now let's come down in the Y direction. And this is going to be pointing that way. This is FAY coming down this way, and this is FA right in here, the force acting on point A. Broken it down into two parts, and the y component is minus 2, minus 4, minus 6, minus 8. What is the magnitude of FA? So when I talk about the magnitude of FA, I'm looking for the hypotenuse right here. Okay, so that's going to be square root of 6 squared plus negative 8 squared. And let's see right here, if I punch that in, 6 squared plus, where's my plus minus on here, 8 plus minus, not that it really matters, equals 100, and we take our square root of that, and it comes out equal to 10. Yes, I know there's some shortcuts. Okay, so the magnitude of FA comes out to equal 10. Okay, there we go. The direction that it's pointing in is 6 minus 8. And like I say, if we simplify that a little bit, the direction could be 6 minus 8, or we could say those both divide by 2. It would be better expressed as 3 minus 4. And there's our 3, 4, 5 triangle, or in this case, a 6, 8, 10 triangle. Very classic one that you'll see me use often when I don't feel like doing a lot of calculation. So let's see. Now, to prevent point A from accelerating, so if we want A to stay put, then we're going to need to have the sum of all the forces equal to 0. And to get the sum of all the forces equal to 0, we can either just say, well, we need the negative FA acting on it, or to figure that out, we can say we need negative FAX and negative FAY. So we're going to call those FB. Not quite up to FB yet. Draw a vector representing a force originating at point A that would counteract FA. So our vector that would counteract FA would go over 2, 4, negative 6, 2, 4, negative 6 right there. And then it would go up instead of down by 2, 4, 6, 8, 2, 2, 4, 6, 8. So what we'd have over here would be negative FA, because that's negative FAX, and that's negative FAY. And of course, negative FAY turns out to be positive because FAY is negative. Negative of a negative is positive. Okay, let's see. FB has a direction of 1, 2, and a magnitude of 4. Draw FB. Okay, so again, this is phrased a little bit differently to make you think about what we actually mean when we're talking about the vectors. I'm going to use a little finer pencil for this one. Okay, so if it's got a direction of 1 over and 2 up, that means that it is going to lie somewhere along that line. Okay, we know the direction that it's pointing in. We just haven't quite figured out the magnitude of it yet. Because it's going to have a magnitude of 4. And I can't just come along here and count 1, 2, 3, 4 points because, my distance of 4 comes out right here. I can measure that, in fact, and say, a distance of 4 measures out to be exactly on my handout. If you've printed a slightly different scale, it might be a different number, but on mine, that's going to be exactly 19 millimeters. Probably should have come out at 20 if I'd printed perfectly to scale, but what we can do right here now is I can measure up (19 millimeters), and there is my vector. I now have my magnitude and my direction for that vector. Okay, so that's where FB would be, and it's not actually on any of those grids or anything like that, because in order to have a magnitude of 4, that has to be on a little circle that comes from this point right here, because this would be a magnitude of 4, and this would be a magnitude of 4, and our magnitudes are all based around a circle right there. Anyway, freehand circle drawing, I think I'm a little bit off on my asymptotes, but you get the idea. All right, let's see, draw FB. To calculate FBX and FBY, let's take a look at figure 5 right down here. Okay, so what we said was FBX and FBY, we gave you the direction, and now we're looking at the magnitude. Now what we know right here is this has a magnitude of 4 and the direction of 1 and 2. Okay, so the first thing we need to know is some similar triangle work. So this should be something that you did in your math class last semester, if not back in grade 10 in high school. I know that's been a little while ago for people coming back into the post-secondary systems, but I distinctly remember teaching this to students in high school. And it's one of the reasons, just to pause for a second, because some of you have done more advanced math are sitting there going, well, why don't you just use sines and cosines and angles? And you might be doing a truss design or bridge building project with your grade 9 or 10 students. And depending on how comfortable they are with math and how far they've got along, they may be comfortable using sines and cosines for the calculations, but chances are you'll end up teaching more math than you do structures. But if you stick to similar triangles, Pythagoras is a concept that's sort of introduced. I seem to recall my grade eights were expected to have had some experience with it. And so if you're doing this with grade 9 and 10 students in a BC secondary school, they should at least have some familiarity with the concept of similar triangles. And one of the things that I do like about what we do in technology education and in the shops is that we can draw those links from our science classes and our math classes and show students where we apply them in real world and make projects with them. It's not all just about making students better at making things, but it's to a certain extent about validating and drawing on knowledge that they already have. Try to break through some of the silos and see where you've got curricular overlap with people in your schools. And you may discover that you've got some alliances and that teachers in other parts of the school are able to help validate and confirm classes that you're doing. And who knows, maybe they'll pick up on a couple of students who really should be signing up for your shop class, but didn't know they'd be interested in it. I've was fortunate to have really good relationship with the science and math departments at my high school when I was teaching there, and I've got to say, uh, they sent some truly delightful students in my direction, and I think it was a net benefit for both of us. All right, so let's see right in here. In here you go through and calculate the hypotenuse of a triangle with height of 1 and 2. So what we're doing is we're saying, well, if I've got a little similar triangle right in here with 1 and 2, then my hypotenuse is going to be 2.24. So if I want to compare that to the big triangle, I know that on the big triangle, this one says 4, and on the little triangle, this one's 2.24. So I just go, the ratio between those gives me 1.79, and so I need to scale this triangle up by a factor of 1.79 to get to the big one. So 1 times 1.79 is 1. That comes out F 3.58. And if you've got any doubts and you want to make sure you've got it right, just run your a squared plus b squared equals c squared on here, and it should come out to 4. So different ways to describe vectors and think about them, but we can always break them down into their component vector. So that should cover enough about component vectors and forces to get you started. We also said that you have to have an understanding of moments, so we want to talk about moments. Okay. Now, moments are what happens when forces act about a point. So, as you know, you take your ruler or something like this and hold it out here, and when you push on the long arm, it's a lot easier to get that to move. You get a lot more torque than if you hold it up close like that and choke right in there. On the other hand, you get mechanical advantage if you come in here because I'm moving a little distance and out here I'm getting a long distance out here. So we're going to be taking a look at a lot of those trade-offs on how doing something with a short radius and something with a long radius are going to affect our moments. Moment is just the fancy physics word for torque. If you've used a wrench, God, I hope you've used a wrench in this program by this point, then you understand what we're talking about with torque. If you sat on a teeter-totter, and I am greatly distressed that teeter-totters are disappearing from playgrounds because I have a feeling, like when I grew up, every playground had a teeter-totter. And, you'd always do the balancing act. Dad would push down on the teeter-totter at one end, and you'd have to sit up close. And as the kid, I'd sit way out at the other end, and we'd balance on there. And so I understand the physics of the teeter-totter. Now they're getting rid of teeter-totters. Something about people launching little kids up into the air with them or something like that. Danger, hazard. But between getting rid of teeter-totters and getting rid of merry-go-rounds, uh, the physics educational experience in the modern playground has been greatly reduced. Right. Anyway, walked uphill to school both ways in the snow. Actually, well, there are no hills really to speak of, but definitely walked to school a lot in the snow. Okay, the moment about point A is written. Oh, gee, look at that. That didn't print out properly. I don't know why. There is a little symbol in the character that looks something like that. So just stop right here and draw that in. That's what we should be looking at. Okay, now if you had to, you could refer to it as M A, but in order to make that work, we need to have the right symbol. And this isn't a Greek symbol or anything like that. It's actually designed to represent the fact that it's a twisting force and not be strange and obscure. This is one of the times you actually get a break and have a symbol that makes sense. Okay, so what we've got right here, there's our letter sigma, meaning the sum of all the moments about A has to equal 0. Okay, so here's our point right here at A, and I've got force C acting at a distance of C and on point C, and here's point B. We've got force B acting at a distance of B. Okay, now you've got a couple ways to keep track of these things because we are going to have a positive moment acting out this way. Actually, that's probably the negative moment. We'll talk about that in just a moment. And a counteracting moment acting down that way. Now, obviously, in order for the teeter-totter to stay level, those two need to be balanced, or else one side's going to be going up and the other side's going to be going down. And it's all going to be spinning about our pivot point or our fulcrum at point A right here. So on both sides, we have forces that point down. So technically, those are negative forces. If we set this up so that this is our central axis to the diagram, then C is a positive distance and B is a negative distance. So this would give us a negative moment in this direction and a positive moment in this direction. Sorry. Such a pain to edit these. I'm not going back to edit that. Just jump back in time 30 seconds. This is a positive distance in a negative direction. This is a negative moment because it is a positive distance multiplied by a negative force. The force is in a negative direction. This one is a positive because it is a negative distance. We've come to the negative side of our fulcrum, and we're coming downwards, which is a negative force. Negative times a negative gives us a positive moment. Okay, now you don't have to worry about that so much because what we can do to keep track of that is we can use this little symbol right here. And so long as you draw the symbol either clockwise or counterclockwise, you're doing great. And that'll enable you to cancel everything out later on. So let's just take a look at this. And the sum of the forces has to equal 0. So let's go through and do a few steps on here. First of all, the moment caused by C, okay, about A. So the moment is going this way. It's going about A caused by force C equals FC times distance C. Okay, and the moment going this way about A caused by force B equals FB times B. Now, because this is going clockwise and this is going counterclockwise, if I add those two together, because they're going in opposite directions, that has to come out to be 0, or else this whole thing's going to start to spin. Okay, so what that means is that I can also say that if FC times C plus FB times B equals 0, I can say FC times C equals FB times B. And then you could do some algebra to go ahead and solve this whole thing symbolically. But let's take a look at putting some real numbers into here and solving this for real. So if FB is 100 newtons at a distance of 0.8 meters, so here we go, 100 newtons, 0.8 meters, and C is a distance of 1.6 meters, what is the moment about point A caused by FB? So that would be FB times B. So force times distance gives us our moment, equals 100 newtons times 0.8 meters equals 80 Newton meters. And you can see here, we've just multiplied the force times the distance. So just as we do that with the number, we do that with the unit, and it comes out, if you've used torque wrenches or anything like that, you're probably familiar with using Newton meters. Okay, and what that 1 Newton meter would be the force of 1 Newton applied at a distance of 1 meter from the center point. 80 Newton meters, that's a pretty good torque. Yeah, I mean, you're wrenching on it if you're putting 80 Newton meters onto something. Now, in order for some of the moments about A to equal 0, what moment must be caused by the force C? Well, if I've got 80 Newton meters acting this way, then I need this one to have 80 Newton meters acting in the other direction. Otherwise, this whole thing's going to start rotating. Okay, so we could call that negative 80 Newton meters, or we could just use the opposite arrow right in here if you prefer keeping track of things by going clockwise and counterclockwise. This works when you're doing it by hand. If you're doing it in a big spreadsheet, you do need to use the positive and negative signs to keep track of them all. What is the magnitude of force C going to be then? Well, we did some of that calculation right up here. I was starting to jump ahead to that. If FB is 100 and B is 0.8 meters, and C is at a distance of 1.6 meters, then FC times 1.6 equals 100 times 0.8. I can say FC equals 100 newtons times 0.8 meters divided by 1.6 meters. FC equals 50 newtons. Okay, hopefully that's sort of making sense. And again, if this arm is twice as long as this arm, you only need half the force out here to get the same torque or to get the same moment. And and this one's twice half the length, so it needs twice the force. The two kind of have to balance out so that things don't get out of control. What is the magnitude of force A? That's an interesting one. Okay. So the magnitude of forces acting on point A has to sum up to equal 0. Now, out here, I've got 100 newtons pushing down, and out here, I've got 50 newtons pushing down. Now, those two have taken control of the rotation because they're at the right distance, but what is keeping point B from accelerating downwards? Something's pushing back up, and that something is coming up through our fulcrum at point A. So the load at point A has to be supporting 100 newtons to counteract FB plus 50 newtons to counteract FC, and that has to be pointing upwards. So, like I said, start with one simple equation, a little bit of simple nomenclature, and we start stepping this up and doing it a bit more and a bit more and a bit more. Now, you will find some questions on D2L that will self-answer themselves and go through and double check to make sure you're doing it right. Get you some easy marks right in there because you can do it as many times as you want until you score perfect. And you're going to see some of the questions are going to look a little bit like this. And just enter the enter the values that you need. Okay, so let's. Well, there's an answer key for this, and you'll get the answer key after you go through and do the quizzes that are on there. If you get a question wrong, make sure you look at the little drop-down menu where I give feedback on the questions, and make sure you use the hints. So there's some questions on D2L. Go through, do those two quick quizzes, and then come back and do this worksheet. Now, worksheet's not so much for handing in. Okay, the worksheet's for making sure that you understand what's going on, which is why I provide you with the answer key. If I was doing this with high school students, I'd probably make them go and hand it in, but this is more of a discussion thing for you guys to go through and make sure you understand what's going on in all of this and bring your questions to me. We're doing this online, so if it's not making sense, email your questions to me and we can get together over Zoom or something like that, or maybe on one of your in-class days and we can have a little chat about it. Take a look on there. And this one, there stays pretty simple. This one is just a repeat of the one that I explained to you, just with different distances out there. This one at the end right in here is taking us to the next level of where we're going to go. And what we're ultimately going to do is we're going to end up analyzing all of the forces in each member of this truss. But what you can do on this one for right now is you can assume that this truss is a solid structure, okay? And you can simplify it down because this force is perfectly vertical. It's going to hit at this point right on here. And so what you're actually calculating now is that you've got a force of 100 newtons coming down here at a distance of 2 meters, and then it's being supported out here by a counteracting force coming up in this direction at a distance of 8 meters. And this is actually going to be the first step that we do in calculating the more complex stresses that we'll be getting to in a week or two in this course, but you may as well jump in right there. Also, what have we got on here towards the end on the last page? You know, if you're rocking through all this and it's making sense and you've done a little bit of this in the past, then go ahead and do these questions. If you're struggling and you look at this and say, I'm not ready for that yet, just slide that page off to the side, hold it for a little bit later on in the course. It will make sense. Okay, we've got people coming into the course with various backgrounds, and you know, some of you have just finished taking a physics course in the last year or two, and some of you haven't darkened the door of a science or a math classroom in over a decade. So, so it will come back. It will make sense, and hang in there, stick with me, and keep giving it a try. If it's making sense and going along easy, go ahead and give this a shot. This was a very practical problem, and I've got video of a robot that looks exactly like this. In fact, our team made a robot like this and headed out to Toronto, competed in Mississauga in the first robotics competition. First being the name of the competition, and they'd been having it there for years. Competed in this in FRC is probably a better way to describe it. And this arm had enough torque to lift the 10-pound load. I don't like imperial units, but the headquarters are down in the States, so they give us these silly values. And we could lift it up in the air, and the robot would be driving around with this, and then actually some of our good friends bumped into us, maybe a bit harder than they meant to, and the entire robot demonstrated this other aspect of physics when the sum of the moments don't quite add up and smashed into the ground, and I wish it had been that slow. When they played it back on Discovery Channel in slow motion, it kind of looked like that, and it was really awesome because, hey, we got our robot on the Discovery Channel, even though we were getting our butts kicked in the process. Then in the next week or so, we're going to be going on and we're going to be taking a look at how do we balance the forces when we have two unequal triangles, and that'll be an intermediate step between going on to analyze the more complex trusses. Eventually, we will get to using computers to analyze the trusses when we get into really complex ones like the ones that I showed you at the beginning of the video. And in fact, we will, if you're interested, be capable of running complete 3D computer simulations, including buckling analysis in Fusion 360. And that's really cool. That's the sort of thing that makes me happy and excited. But in order to get there, we want to focus on some of the basics to begin with and start talking about how these forces come together in the hopes that when you start analyzing structures and looking at how things work, that you'll start asking yourself, oh, how do those forces cancel out? How do those moments cancel out? Where does the force flow through that structure? Until then, may the force be with you.